And now I give the floor to Dr. Muhymin Islam to give his perspective on working in Intel or the semiconductor industry.
Today, I'm going to talk about my experience in the semiconductor industry. So I'm not sure like whether the experience is pretty like exciting. Yeah, definitely it's exciting, but I'm not sure like whether it's pretty enjoyable or not. But yeah, there's some advantages and disadvantages. That's why I use this demo here. And basically, I'm working in the semiconductor for a while. I'm not like very experienced like Omar. I have worked in different fields so far. Like I started working with biosensor, with biological cells. And then at some point I started working at FET, I mean, FinFET or planar FET, etc. And currently I'm working on PICs like, we mostly call it like silicon photonics, but some people call it like photonic integrated circuits, so PIC. So I work in different places, and so that you understand, like I'm not like expert on anything. And some of the things I will share today, everything is available for in public domain. I have tried to put all the links and reference. Some are available in papers, some like in different technical magazines or scientific magazines. I have taken something. So all these are in public domain, nothing is secret. So if you want to learn more about it, you can just Google and get some more information about everything that I will share. So let's start. I think it's not working. Let me just, can you see my screen is changing? No, right?
No.
Let me just do something. Okay, let me just do something then. It's better because I'm working with two monitors and that might be causing problem. Okay, can you see my second screen now?
Yes.
Okay, yeah, the double monitor was creating some problem. Okay, so here is some basic introduction about me. Like currently I'm working as a quality and reliability engineer and mostly focusing on silicon photonics. Before that, I worked as a device engineer. At the time, I had opportunity to work on like some advanced node FinFET. I work on FDSOI to some extent and also on technology. So those are like all related to logic. And before that, I work on cell manufacturing as a postdoc in Georgia Tech, and my PhD was also on biosensor for cancer diagnosis. And before that, I did my bachelor's from BUET in electrical engineering. So you can see like there's, I mean, you can find some correlation among all the things I have done, but basically there is not much correlation, I guess. So I can like make an analogy like our food habit here. Like as you have seen, Omar has started his undergrad thesis in semiconductor and he kept working on semiconductor, right? So he had the privilege to do what he likes, right? And sometimes we do the same in our food habits. We just keep eating our favorite dish, but not everyone has that opportunity. So some people like have to try whatever they get, right? So I kind of see my professional career is like that. I'm like jumping from here and there, and I'm trying to get any opportunity that I get. So I think that's also pretty interesting because I had opportunity to explore different things. So now let's jump into semiconductor. I will try to like talk a little bit about my experience in my PhD and postdoc. It's not exactly related to semiconductor, but maybe I'll touch up something if I get enough time. But I would like to start about the semiconductor. So when we talk about semiconductor, we usually think about like planar FET, FinFET, gate all around FET, right? We talk about like nanosheets and nanowire. So this is the typical picture that we usually see, and like we know like TSMC and Samsung, they are like in a race of making like 3 nanometer, 1 nanometer, etc. But what we usually don't like think about semiconductor is silicon photonics, right? So Intel is interestingly working on silicon photonics. I did not even know that, like maybe before here, like Intel works on silicon photonics, but I came to know, and now I'm working on that. And there are basically like, if you search like scientific magazine, or even if you go to Intel's website, you'll see like they have many information about silicon photonics, what is the state of art and what they are trying to do. So we'll find plenty of information. I have like some link here, a couple of links. The first link, I think it's related to like logic, like how we are moving in the logic industry, like from FinFET to gate-all-around FET to nanosheets, etc. And the second link, I think it's about silicon photonics, and mostly about Intel and some other company who are working on silicon photonics. So I feel like I was not very familiar with silicon photonics, why we do that. So I would like to show this video so that you can get a basic idea like why we use silicon photonics, or why Intel and some other companies working on silicon photonics. It's mostly the application is in the data center, but I think instead of talking much about that, if you see this video, that will help you to visualize like why we are using like silicon photonics. So let's watch this video. It's a small video, like maybe 2.5 minutes. And then I will come back to my presentation again.
Data is growing at a staggering rate from an ever-increasing number of types and sources. In fact, 90% of the world's data was created in the last 2 years alone. This explosive data growth is placing extraordinary demands on networks, with 5 times more traffic occurring within the data center compared to total internet traffic, requiring large-scale data center operators to deploy higher-speed connectivity over greater distances, which can be longer than several football fields. To meet these demands, a massive number of high-speed optical transceivers are deployed to connect switches, converting electrical data to optical signals that are transmitted on fiber optic cables over distances from hundreds of meters to several kilometers. However, these transceivers are often expensive, and traditional optics manufacturers have struggled to keep up with the unprecedented deployment size of hyperscale data centers. But Intel Silicon Photonics has changed the game by integrating optical data transmission with Intel's world-class silicon manufacturing, enabled by the world's only hybrid silicon laser. This breakthrough technology converts silicon-based electrical signals into light, enabling data to be transmitted over great distances at ultra-high bandwidth in today's hyperscale data centers. And with multiple 100 gigabit products shipping in high volume, Intel Silicon Photonics delivers a cost-effective solution for faster connectivity over long distances to maximize hyperscale compute utilization. Intel Silicon Photonics is also expanding beyond the data center with products for 5G wireless connectivity for communication service providers. And in the future, Intel Silicon Photonics products will drive a significant increase in bandwidth and will provide even greater levels of integration with silicon, dramatically increasing system performance with higher density, lower latency, and lower power. Intel Silicon Photonics, breakthrough network technology for the demands of hyperscale data centers today, with compelling innovation for the future. To learn more, visit us here on the web.
Okay, so the YouTube video link is here. So if you want to watch the video, if you have any problem with the sounds or video, you can watch it again if you're interested. So that will give you some idea like why we are using silicon photonics. So from this, what I want to highlight, like the whole purpose of silicon photonics is to use for communication. We want to use like light, right, in simple words. So we have laser, we have modulator, mux, demux, and then we have photodetector. And basically here we have 2 parts. One is like transmitter chip, which like use laser to convert electrical signal to optical signal. And then we can transmit the information to some extent up to like 2 kilometer or 500 meter, like different distance we can transmit it to. And then we have a detector chip. It basically collect the light that it sent from here, and then it convert the light again into electrical signal. And in that way, like we can transmit information using light. And as a QNR, I mean, I work as a quality and reliability engineer. So for silicon photonics, like laser is kind of, I would say, the backbone of the whole chip, right? The most of the issues that are expected to come from laser. And when it's about reliability, laser is maybe the major bottleneck. We don't see much issue with the modulator or marks, or even the photodetector works pretty fine, but we see many issues with the laser. So I will talk a little bit about the reliability of the laser, and all these things are like, if you search in Google Scholar, you will get plenty of research paper journals and conference papers on laser reliability, laser performance. So in that way, you can learn more about it, but I will just give you some very basic idea for that, hopefully. So let's start with logic first, because I started my career as a device engineer. And what does it mean? I'd like to share my very own experience, because when I joined as a device engineer, I did not even know like what device engineers means or what a device engineer does, right? So I joined in GlobalFoundries and then started working on device engineer, but it took me like several months, at least several weeks, to understand what device engineer means. So I'd like to give like some work that we do in day-to-day basis as a device engineer, so that if anyone is interested, you can know like what skills you need or what you need to know as a device engineer. I hope everyone can hear me, right?
No. Yes.
Okay, great. Yeah, it's very quiet, so I thought like everyone has left. Anyways, so as a device engineer, what we need to do, right? You can work in pathfinding, you can work in high volume manufacturing, you can work in technology development. I think the role might vary to some extent, but more or less the idea might be same. I have worked limitedly on like technology development and high volume manufacturing, mostly in high volume manufacturing. So pathfinding might be a little bit different. But overall, as a device engineer, we have to ensure, like in simple words, we have to ensure like our transistor will give the desired centering and performance. In very simple wording, I do not want to make it complicated, just to give you a basic idea. What does it mean? What is meant by centering and performance, right? That I'd like to mention. So before going to that, let me talk a little bit about like planar MOSFET or about a FinFET, right? These are very common structure you will see in Google, right? If you just Google with FinFET or MOSFET, you will see this kind of images. Those are taken from Wikipedia. These I got from some website, I guess. It's like basically like high resolution image of a real planar FET. That's real, I think it's a TM image. So what happened in, whether it's FinFET or it's a planar FET, it has source, drain, right? We all know about that if we have some background on reading on like taking electronics, advanced electronics, or maybe basic electronics 1 and 2, you will know like we have source and drain. Then we have gate, and then we have body, and between gate and source, we have a dielectric, right? FinFET is kind of same. We have gate, drain, source, but FinFET is 3D, right? It's like we create the fin on the silicon to make the FinFET. But overall, we have like basically junction, which we can source and drain. FinFET, we have additional fin, which is not present in planar FET. We have gate, we have contact, we have to connect the drain, source, and gate, right? We have contact. And then we have metal stack, like interconnect, right? We have billions of chips, as Omar has mentioned, and we have to connect those. So all these things can contribute to the device performance and centering. Now, what is mean by device centering and performance that I like to mention? Here is a simple like plot I would like to use to explain what is device performance and centering. So we all kind of know, right? A FinFET or any transistor has basically drive current and leakage current, which I can say I off, that means off state current, which we can also say like leakage current. And we have drive current, that means what is the current that we get when it's in on state. Centering means, I interpret centering as the amount of drive current I'm getting from a transistor. And performance means how much drive current I'm getting at a given leakage. Because for a transistor, we can keep increasing the drive current. Maybe to some extent, it's not a big deal, but what will happen, your leakage will go up. So that may not help you if you have too much drive current and too much leakage. Eventually, you will get the same performance. So here is 3 lines that I try to show. Like say, for example, I have a target at a given drive current, given leakage, I have to get a specific amount of drive current. Then this is my target performance. If somehow I can get higher drive current at a given leakage, then I will say my performance is improved. And for some reason, if I get like less drive current at a given leakage, then I will say my performance is decreased. Definitely by shrinking the device, when we go to advanced node, by shrinking the device, we try to minimize the area. At the same time, we are doing all these things to improve the device performance. Like for planar FET to FinFET, we have moved here because we have more control on the leakage current. At a given leakage, we can get more drive current. That's kind of a motivation to move from planar FET to FinFET. There are some other motivation, but that is one of those. Then let's talk a little bit more about that, like what we need to know, like as a device engineer, or what we deal with. First of all, I would say like it's very important to understand the device physics. Now, there is no upper limit or lower limit, right? I'm not like expert in device physics, but when I started working, I was able to know like many things. And so yeah, it's like a never-ending process, because I have worked with people like who are working just as a device engineer for 20 to 25 years, and I have came to know like they're still learning, right? So it's kind of like endless journey. You can learn as much as you can, and still you can explore new things. So device physics is very important. Like the better we understand, it's good. Then understand the process flow, like the process flow for like FinFET or advanced node FET, it's very complicated. Like when I was exposed to the whole process flow of a FinFET, I thought like, okay, it's not gonna work. Like how they make it work. They make billions of chips using that very complicated process flow, which takes around a couple months from the scratch to the end, and still it works, right? So it's kind of amazing. Like when I saw that, it's like more than a science fiction movie to me. Like it's very amazing. Like I was like very surprised to know that they make for a single chip they have to do that amount of steps. But as Omar has mentioned, we make millions of chips. That's why we can afford, like even if it takes 2 months, we just don't build one transistor by one transistor, right? We make like billions of transistors at single shot. That's why we can afford that. Now, for understanding the process flow, it's basically like some of the process steps we do repeatedly, right? Like lithography, etch, deposition, epi growth, ion implantation, and annealing. So even if you have taken some courses in your undergrad or grad class, I think you could have learned slightly about this, at least to some extent, about all this process flow. Like I remember I took a course in PUET, like semiconductor fabrication, and then I came to know at least the theoretical background of this process flow. So it's as a device engineer, we need to understand this process flow, because otherwise it's hard to design your device so that you can get the desired performance. Here is basically some cartoon. I mean, it's very simple. I mean, they have just shown the process flowing only in few steps, but it can give you some idea like how it works. Like here is basically a typical FinFET. It has like junction, it has metal gate, it has fin, etc. Right? So how the process works, first they take a silicon and then etch the bulk silicon to create the fin, then add some dielectric to like cover everything except the top of the fin, and then we do more steps, and at some point we create the junctions, which is basically source and drain, and then we create the gate. So that's basically like in semiconductor, we say like the whole process flow is divided in mostly like, it can vary to some extent, but mostly it's like front end of line, middle of line, and back end of line. So mostly when we make the transistor up to the metal gate, or maybe up to the connection to the metal gate, to the first metal layer, is called like front end of line and middle of line. And then in the back end of line, we do all the interconnects. So this is just the process flow up to the front end of line, I will say. And here is a like TM image again for FinFET, like it's showing like how it looks like. If we see the top view, we have source and drain, and we have gate, and all these lines are FinFET. In one FinFET, you can have multiple fins or single fin, it depends on, right? So it's showing like there are 4 FinFET. So it's important to understand the process flow and device physics. At the same time, if we understand both of these, then we can understand some of the things that are very important for a device engineer to understand. And it's basically ET correlation, ET inline correlation, inline correlation. I will try to talk a little bit more about that in the next slide. Here is a figure that I would like to tell how much detail we need to understand. It will give some idea. Like here we are just showing, like this is a paper from SY. Basically, I had opportunity to work with him. He's a nice guy and he knows a lot. Anyways, so here is a TM image of a FinFET. You can see this is source drain, or we can say it's a junction, and this is a fin, and we have a gate. So you can see like just in this small place, and these are all nanoscale, right? As Sabi has mentioned, like now we work on 10 nanometer, 14 nanometer, 7 nanometer. Within a small place, like in a very small range of place, we have different type of capacitance. I'm not talking about anything else. It's just like parasitic capacitance. We have capacitance between fin top and this is metal line. So we can call it middle of line capacitance, right? Then we have capacitance between source drain and bottom of the fin. We have capacitance between junction and top of the fin. So in a small place, we have very complicated things going on, right? In the small scale, like we sometimes say like short channel effects, etc. Now, we know all these things are happening, right? If we read like semiconductor basics, you will know like all these things, right? You will see some diagrams. But to understand those things or to measure those parameters, it's also very complicated, right? Like, for example, can we make a transistor and then go and measure this middle of line capacitance? Maybe no, right? So we have to come up with some structure, electrical structure, that is not exactly maybe the exact FinFET that we are using in the chip, but we have some electrical structure that we make and put in the wafer in some places where we don't have the actual dies, and then we measure the structure in different ways so that we can decouple all this capacitance. So that is very exciting and interesting part of a device engineer to create the test structure, to design the test structure. How can I measure this middle of line capacitance? How can I measure this CFP, right? All these things. So we have to come up with some structure. Also, we have to define the test condition, like how we are going to measure those structures so that we get the real capacitance, right? Like if we make a structure that can have some other parasitic capacitance that will not represent our real transistor. So we have to come up with a test condition and test structure that will give us a value which is more close to the real world transistor, right? So defining the test structure and the test condition is important, and how the testing is done, that's also important. So as a device engineer, we have to deal with, like, I mean, not only as a device engineer, like if we work in any part of the semiconductor, there are like many groups in a semiconductor industry because it's a very complicated process. So we have to work with many people to understand the things, because it's not possible for one group to do everything. But we have to know as much as we can so that we can understand if there is a problem, where it is coming from, and how to solve that. Now, here is a slide. I can quickly go to the ETT correlation and all this correlation, right? We, as a device engineer, we have to like deal with so many data. Like, say, for example, when we have a transistor we build, sometimes we have to check like thousands of parameters, like, okay, what's going on? If we see a problem, or if we want to do a performance improvement, we make a design of experiment, we implement that, we get the data. Then I have to check thousands of parameters just to know, like, okay, I'm improving my drive current, or I'm improving my leakage, but I'm not compromising something else, right? So it's very critical. So it requires like a lot of data analysis to understand that. So one thing we do, like ETT correlation, the better we understand the correlation between different, like we have maybe hundreds or thousands of ET parameters. If we understand the correlation among them, it's very helpful, because then we don't have to check maybe the thousands of parameters every time. You can just select like your 50 key parameters, and you can quickly see the lots, how they're doing. And if they're okay, you can say like, okay, maybe my remaining 900 parameters are fine, right? Then ET line correlation, it's interesting, like we have the long process flow, right? And as Omar has mentioned, we have a like variation. You will not always get the 10 nanometer gate length or 5 nanometer thick gate oxide. So we have a natural variation in the process flow, and sometimes we have some excursion, and we have like larger variation than we expected. So that's why if we need to understand how much process flow variation can contribute to our key ET parameters. So for example, I have I effective, which is basically I drive current maybe. I mean, if you want to know about what is I effective, there's some papers, like they define what is I effective. It's not exactly drive current, but we apply some voltage. There is a test condition, specific test condition we apply to get that, to calculate this I effective or effective current. So now effective current can be impacted by the doping concentration, the amount of doping we are using in the junction, in the well, etc. Right? So we need to know what is the correlation, because if we want to improve our device performance, we have to know, can we change our doping concentration and get better electrical performance? So if we know the correlation, that will help us to design our experiment. Then there is a, and even with source, this is just another parameter we can consider. Like, as I have shown, there are different modules, right? FIN, junction, gate, right? Everything can contribute to your critical electrical parameters. So we need to understand the correlation with every part, and then we need to understand how to decouple it, right? If you see like my I drive current is different, then we have to understand whether it's different because of like junction, or because of gate, or because of gate oxide. So we need to understand, that's why we need to understand all this correlation. Another interesting part is like inline, there is a correlation. Say, for example, I want to make the fin, right? First I make the fin. I want to have a fin with a height of X nanometer with width of Y nanometer. But I will not always get that, right? I may get like 11 nanometer. Then what will happen, like your source and drain will be affected by the change of CD of the fin. I mean, if the critical dimension of fin is changed, consider like, okay, if my fin goes off, or for example, if I want to improve my device performance, if I change my fin CD to some extent, then how my junction will be changed. And based on that, we have to like deconvolute how much both of these will affect in the drive current, right? So we have to deal with very complex model to understand all these correlations. So that's one thing like a device engineer spend to understand all these correlations. So that's a major thing we have to deal with. And then let's talk a little bit about the test structure. Like if you have taken any VLSI course, like I took one from in the BUET. So I came to know like some layout and schematic of a device, right? Using cadence or K layout, you can design a schematic, like it's a simple inverter, and then you can make the layout. So we need to understand these things like, sorry, I don't know. Okay, so as a device engineer, sometimes we need to make our own structure, as I have mentioned. Like if I want to like measure a capacitance, I have to make a structure for capacitance. If I want to measure resistance, then I have to make a structure. Some structures are easy, sometimes it's complicated. For example, if I want to measure a resistance for interconnect, right, what I can make a simple structure like with length A, area A, and right, and then we can measure the resistance because we know R is equals to rho L over A, right? Something like that. It's very simple example. But we can have more complicated structure to understand the layout effect sometimes, because we never use a single transistor, right? In real world, we always make like billions of transistor and try to understand what's going on. So in that case, many things affect that, like how many if one transistor is surrounded by thousands of transistors, its performance might be different than a single transistor, right? So we try to mimic the structure, like we always make an array of transistors, so mimic the real world chip. And also many things affect, like some of the parameters here is shown. It's an article, I think I got it. It's published by GlobalFoundries. So they have explained some of the things. If you are interested, you can go and look a little bit deeper. So one is the key parameter, like one of the key performance driver is like CPP. CPP is basically the pitch or the distance between two adjacent gate. Then fin pitch is also important. Fin pitch is like what's the delta like what is the distance between two fin, right? So not only the gate length is crucial, also the distance between two gate, distance between two fin, these are really important. And when we design the structure, then I don't know, maybe some of you are familiar, taking the VLSI, like we have to do some steps. We have to follow the design rule check, right? For every technology in the industry, there is a design rule check. You cannot like make this fin pitch as low as you want, right? There is a limitation, process limitation. Like maybe you can suggest like, let's make the fin pitch like 2 nanometer, then device performance will improve. You cannot do that, right? Because it's not possible to implement 2 nanometer device to fabricate like a transistor with 2 nanometer fin pitch. So that's why we have a design rule that we have to follow, like we cannot go below that critical dimension. And when we do after making the layout, then we have to do layout versus schematic check, right? Whether I'm getting what I'm expecting. And then after creating the structure, we have to finalize the test condition. We have to talk to the test team, like there is a specific test team, they will measure everything, but we have to tell them, hey, for this structure, I need you to apply 5, 4, or 3 volts in the drain. I need the body to be grounded, or I want some biasing in the body. So as a device engineer, I have to give all the condition to the test team so that they can measure, and then I will analyze the data and say like whether it's meaningful or not, right? So that's important, I would say. Then let's go what I do as a reliability engineer. Can you hear me still? It's showing like my
Yes, audio got a bit choppy in the middle, but now it's better.
Okay, great. Yep, thanks. So what is reliability engineer, right? Now, how we define the reliability, right? Like sometimes we say like, hey, this news is not reliable. Like once I heard like Angelina Jolie is converted to a Muslim, right? But that was not a reliable authenticity, right? In semiconductor, reliability is used for different purpose. Like it's, I mean, it's just my definition. You can say like, hey, it's not right. You can contradict with me. But my simple definition is how long my performance will be within spec. Simply, I can say that. Or in one word, I can say longevity. That means what happens, like if I make a transistor, maybe its performance is okay, right? It's giving you the desired drive current and leakage that you are willing to get. But it might happen the device may stop working after 6 months, right? And that's not good. Like if you buy a mobile phone and you can, you know, right, there are billions of transistors in the mobile phone, right, in one phone. Now, if one transistor stops working, maybe your phone will stop working, right? So we want to ensure like it will work, all the transistor will work at least for 1 year or 13 months so that we can pass the warranty and then we don't have to take the responsibility, right? So after 30 months, if it goes bad, maybe it's fine. But anyways, so that's kind of the goal of our reliability engineer, to ensure like, okay, the performance will be stable at least over certain period of time. And in order to do that, okay, let's talk about this. Maybe this is very basic of reliability engineer. Everyone talks about this, like Butler curve, right? Like when we make like some transistor, it's showing like the fail rate over time. Say, for example, if you make billions of transistors, some will stop working at very early stage, those we call infant mortality. We try to always reduce that using something. We try to screen out the bad devices, etc. But then there will be random failure that's very hard to control because, you know, some will fail. We don't know, right? Not every transistor is good. Some we can screen out, but still we see some failure over the period of time and it's random. And then at some point we will start to see wear out, right? Because nothing will last forever. So in that case, we always talk about DPM. I think it's a generic term. You will find some literature how to calculate it or what does it mean. It's basically defective parts per million. That means we have to make a calculation. Like if we make 1 million transistor, how many transistor will be bad? I mean, how many transistor will not meet our reliability goal? That means they will stop performing before a certain period of time. And usually like DPM target can be like 500 parts per million, right? So if we make 1 million transistor or 1 million chip, we have to ensure like not more than 500 transistor will stop working. So it's very critical, right? You can see like millions of transistor we are making using like a long process flow rate may stop working and remaining almost million will keep working for over a certain period of time. So it's very interesting, like how can we ensure that and what testing we need to do to ensure that. So in order to do that, usually we apply stress condition like elevated voltage, current, temperature, humidity, right? Because we cannot make a transistor and keep using it for 2 years. Then I will say, hey, this transistor will not burn out in 2 years, right? So instead of that, we apply like elevated stress condition and we apply the stress condition for a certain amount of time. Say, for example, if I apply 5 volt in a transistor, whereas the operating voltage is maybe 0.8 volt, and then apply the stress for like maybe 1 week, and maybe I'll apply some elevated temperature because we are budgeted, right? For example, like I apply temperature of 100 degrees Celsius. From that, maybe I can say like, okay, this transistor will work for 3 years. So there are different mechanisms, like it's a failure mechanism from logic, like HCI, you can get materials. Sometimes multiple mechanisms can affect. This is very important to define the stress condition, also the probability of failure, which is like, as I mentioned, how many can fail. And also we have to come up with the sample size, right? Like how many transistor or how many chip we can test or we should test to ensure we will meet the DPPM goal of statistics here. And interestingly, reliability statistics and performance statistics is very different. Like for performance, the way we calculate the performance is pretty linear type statistics, but for reliability, we use like different statistics, very commonly used Y pool and log normal. So if you ever want to be a reliability about this. So here is a simple example like that I basically do maybe every day now, right? As how to ensure the laser reliability. So laser, it's a simple LI curve for laser because we know about the transistor, right? It's kind of leakage, drive current, etc. For laser, what is laser? Let's talk about laser first. Laser is basically a stack of conductor material, different types of material that we stack on each other, maybe 5, 10, 15, 20 layers are there. And then there is active zone, which emit the light. So, and we have contact. So, and plenty of literature to understand laser, what's going on, what's the state of the art, different types of laser, etc. So in general, in short, again, if I want to see it like in a simple word, we apply a specific bias current and then we get optical output from the laser. And this graph is called LI curve. This is basically the everything in the basic about laser. So we always want to get a desired current, desired optical power as a given to get the lasing. It's called threshold current. Same like threshold voltage concept, right? The concepts are kind of similar to some extent to logic or like transistor. Now, the green one is maybe a nice LI curve, which is showing like, I don't know why it's this. It's showing the laser is fine, but these red lines, those are like, I can say like those are bad lasers because you can see this is kind of kink. It's not giving me what I expected. And this red dotted line, this is like completely a bad laser. Maybe it's not working at all. So now how can we ensure the laser reliability? What type of test we can do and what is the failure? Because that we have to understand it. So one common mode of laser reliability or laser failure is COT, which is catastrophic optical damage. It's come from the defect from the crystalline structure of the laser, because you will see like there are like all the materials we are using for laser, it's complicated, right? Always is tertiary, or sometimes we use 4 different materials, alloys. So all this crystalline defect can cause like laser failure and mostly catastrophic optical damage. There are some other failure mode. If you're interested, you can learn from literature. Now, how can we detect those mode early? We have to again apply like simple elevated temperature, current, or voltage, etc. Right? And we try to detect, ensure the laser reliability will be okay. Here is some graphs I got, like some images I got from literature showing what is called. Like here is a laser, you can see like the light spot here, you can see like there's a bright spot, you can see wide, it's nice, uniform. So it's a good laser, but you can see there is a spot here. So I can say there is a defect, right? So it has quad type of defect. And if we do that TM, or I think this type of image we can get from IRAM or SCM, but this type, like we have to do the TM to get, I think it's IRAM, not SCM, but it can be different. Sorry, I'm not sure exactly, but then we have to do TM. Basically, we want to see the crystalline damage, then we have to do TM, because then we can like go in very small scale. Like you can see this is 500 nanometer, then you will see like it's bad, right? You can see all the images, and you will see many other different types of catastrophic optical damage images. And one of the things you can see, like another image showing there is a molten zone. So your laser has been molten, there is dislocation, etc. void. These are all kind of like damage we see in the laser. So now overall, what we need if you want to work as a device engineer or reliability engineer, definitely we need to understand the physics. Then to design the structure, we need to understand the layout, like we have to use cadence and K-layout, and then understand the testing, fabrication process flow. One thing I'd like to highlight, like characterization is important, because you have seen, like have shown like some images, TM images, and we also do like some other high-tech characterization process like CMEDS. I'm not sure like why I dimmed it the color, because all other things maybe we can learn even in our undergrad to some extent, but this characterization, I'm not sure like in Bangladesh how it's, or in some other countries like in undergrad, how we get opportunity to use this type of characterization process. But rest of the things we can at least learn to some extent in our undergrad. Now, one thing I would like to highlight, like as you have seen, we need the statistical process control. We have to do a lot of data analysis. One thing that I use almost every day, like this is the key thing that I use, that is JUMP. So as a device engineer or reliability engineer, we have to do a lot of data analysis. A JUMP is commercially used in different semiconductor industry. In many places, JUMP is used by many industry or many field. So if you have any opportunity to learn JUMP, I would say like just take it, because it will really help you to analyze like volume data. That means it's helping me to analyze volume data. It's very important. I think that's, if you don't understand device physics or anything, if you just know JUMP, I think still we can survive. So that's very important. And then especially statistical process control, like Sabi has shown, like it's very important. Like we maintain, we have a control with all the process flow, all the ET parameter we have. So we need statistical process control. And then we have, it's very important, model-based problem solving, decision making, and communication. These are like peripheral skills, something that we need. So model-based problem solving you can learn in Google, and if you're interested, you can take some statistical courses wherever you can. It will give some idea. So these are very important skill set that I am trying to have, because I think this skill set I need in my day-to-day work. Like maybe I don't have to do SCM team, but I have to understand like how to read an SCM image or how to read an TM image. So these are very important. So I think I have already taken plenty of time. I will just quickly go through what I have done in my PhD. I basically work on surface engineered biosensor for early detection of cancer. It was my dissertation title. So I basically come up with a cool biosensor which can be used to detect cancer cells from blood of a patient using some ionic current measurement. I don't want to go into detail because I spent, or I don't know, 5.5 years just to do that. So I don't think I can explain it even in 10, 15 minutes. But anyways, that's the basic idea. Like I wanted to detect cancer cells from blood. And here is a nice image. I like this image. I took it using AFM. It's basically the surface image, because I created some kind of random structure in the surface, and then I use some biomolecules to capture the cells. So I have like combinatorial approach. I use biomolecules to capture the cells. I also use ionic current measurement to detect the cells as a secondary approach, and combinatorial approach gives me a significant cell detection ability from a biochip. So plenty of work is going on in this field. If you are interested for research, you can work on like all this logic, or you can work on laser, something like that in silicon photonics. But if you are interested, it's a huge field to work on, like cancer detection using biosensor or cell manufacturing biosensor. And this is a cell image using SEM. So I have used some kind of like characterization devices in my PhD to characterize my device. So that basically helped me to some extent. That's kind of a correlation with what I'm doing now. Like I know I have used these characterization tools that still I need to understand like how things work. But yeah, not much. And then I work as a postdoc in Georgia Tech. I work on cell manufacturing. That is a very interesting term. I did not even know this term when I did my PhD. I never introduced to this word. I think it's very new. I mean, at least when I started doing my postdoc, I came to know like people are talking about cell manufacturing, especially in Georgia Tech. It's very important. Like we talk about like semiconductor manufacturing, right? Because those things are stabilized. We have a standard, we know how to make a transistor, and we know what should be the performance, what should be reliability. But when it's about cell, there is no standard of cell. We don't know like what is the benchmark for a good cell or bad cell, right? So there are a lot of work going on in this field also. I especially like to highlight CMAT. I have the link here. When I was in Georgia Tech, they basically developed a organization within a Georgia Tech, and most of the Georgia Tech bio professors and professors from electrical, mechanical are part of this institution. They are doing some really good works, and I really hope like they will do something amazing in future for cell manufacturing. They are working excellent work. So if you're interested, you can go to their website and see what they're doing. So basically, I work on a ridge-based microfluidic device. It's basically a microfluidic device. You can see it's like a tunnel with many bumps, right? So we pass the cells, and when the cells come under a ridge, it basically compressed, and when it goes out of the ridge, it gets like, you can see it's compressed, then it's relaxed, it compressed, relaxed. And this device can do several things. It can sort the cells. If based on the cell stiffness, the cells can go in different ways. And we know like healthy cells, cancer cells, they have difference in cell stiffness. So if they are passed through this microfluidic device, they can go in different direction, and we can collect the cells from different outlet. And that kind of give us an ability to sort the cells. Also, when the cells are compressed, some pores are created, and that's an excellent vehicle to engineering the cells. Because when the pores are created, if you have some biomolecules, they will go inside the cells and they will retain in the cells when they will come out of the device. So here is a image where we have seen some biomolecules, and that's why you can see the color difference. So that's an excellent way to engineering the cells. And I've done some interesting work here. Some of the links are here. So one of the work I did, like I treat the cells with chemo and sort them based on like stiffness difference. And then I came up with a pathway, like why the chemo treated, some of like we know about like chemotherapy, right? Some of us, we are familiar, like when chemotherapy is applied to a patient, sometimes it works, sometimes it doesn't work, and patient to patient we have to vary the treatment. And that's, I think, about like precision medicine. So precision medicine is interesting thing. Like we think like every cancer patient is different, and that's why everyone needs a unique treatment, because the path, okay, I think, yeah, that's basically that, yeah, of precision medicine. So I took some cancer cell line and treated with chemo and sorted the cells, and then I tried to investigate why cells become chemo resistant, why it doesn't work. And I came up with a unique pathway. I mean, it's very hardcore biology. Maybe I could not even understand everything, but some of my collaborators, they were very helpful, and we explore an interesting thing over here. So that's pretty much about it. I'd like to say what motivates me. I'm working in a different field. It's hard to cope up with these things, right? So here is one of the motivation that I always feel like. Here is a painting from Van Gogh. It's in the display in Metropolitan Museum of Art. It's a nice museum. So he just painted a pair of old shoes, right? And now it's displayed in Met. So you know, and one of the things that I like from Nietzsche, I think it's from the book Good and Evil. I really like this work. Like I came to know like about this quotation this maybe months ago, but I always feel that like, okay, it's not about success. It's just I try to enjoy what I'm doing. And another interesting thing I'd like to mention from Harari, he gave an interesting analogy. Like now we are moving so fast, technology is moving so fast. Previously we learned something and we can work on a same field forever, right? But now it might be relatively harder because things are moving so fast. So he thinks it's most important is to have emotional intelligence and mental resilience. So what does it mean? It means like we need to have the capability to adapt with the change. That's something. He gave an excellent analogy. Like he mentioned, like previously the goal of our education was to build a stone house and live there forever. But now we want to learn how can I make a tent, live somewhere for a while, and then move to another place where whenever it's needed and start to live there and do something different. That's I like about it, because even if I talk about the semiconductor industry is moving so fast, and I'm not sure like what will happen in the semiconductor industry after 10 or 15 years, whether we will still focus on logic or we will completely move to bio-related things. Like, as I've mentioned, like I have worked on bio things. Those are not maybe in the mainstream of the semiconductor, but I know some of the semiconductor industry, like on semiconductor, I have seen like they are doing amazing work on some bio things, right? And you'll see many things are going on the bios in the semiconductor industry also. Maybe at some point, all the company will start to focus on. So we never know what will happen after 10 years. Maybe things will dramatically change. That's why I think it's good to like just to learn new things, explore whatever opportunity I have, and yeah, just keep moving. Let's see what's waiting at the end. That's pretty much it for me. Thanks for listening to me, and sorry if he like did not help you at all, but yeah, that's all.